The next topic we're going to do is Newton's laws. This is new this year. It's building on force summation, projectile motion, and balance and stability that you've already done. There's three laws that Newton wrote about. So the first is inertia, second is the law of acceleration, and the third law is action-reaction. So Newton's first law is looking at an object and just describing it as staying there unless a force is applied to it. So that object being the golf ball in this picture here we have here with us. There's the golf ball if you can see it. That will stay there unless a force is applied to it. So an object will stay at rest, or it tends to remain at rest unless acted upon by some external force. What is the external force with this apple falling out of the tree? Can you remember? I hope you've come up with gravity. So Newton's first law of inertia means that if an object is moving, it tends to keep going unless something stops it, like friction or gravity. Or, as in this picture here, we have that big guy in this rugby tackle. And also an object that's is stationary will remain stationary unless a force is applied to it. Here we are, we've got Newton's first law, and an object will keep moving unless something stops it. And here we've got our little guy who is on his motorbike, and the brick wall has stopped his bike moving, but he has kept going. So Newton's law has stopped the bike, the motorbike, but because he hasn't hit the brick wall, he's gone over the top and he's kept moving in the direction he is travelling. However, what's going to bring him down? What stops him keeping going forever? I hope you've come up with gravity and air resistance and all those things. The first law also means an object that is not moving stays put unless something hits it, pushes it or pulls it. E.g. our guy lying on the couch. He's in a state of inertia. Or the golf ball. That's not going anywhere either. How about we consider Newton's first law being applied to a basketball jump shot? That basketball will stay in his hands unless a force is applied to it. So it's not going to go anywhere unless he applies a force to it, which he does. So he applies a force to the basketball. The basketball will then travel towards the goal. However, the basketball will keep going in the direction that it was sent unless another force acts upon it. And again, the force acting upon it is gravity. So that will change its direction of travel. In your workbooks, turn to page 66. Okay, just answering the first question there. An object will stay at rest as long as nothing pushes or pulls on it. An object in motion will stay in motion in a straight line unless something pushes or pulls on it. The first one is, this resistance to a change in motion is known as its inertia. I hope you've got that. You could go on now and answer question 2, 3 and 4. Question 2. Consider looking at the two sumo wrestlers, who is likely to have the greatest inertia or resistance to change in motion, and explain why. So looking at that, we can see that it's the little guy pushing the big guy. So the larger wrestler has greater inertia as he has a greater mass. And question 3, having a great deal of inertia can be both an advantage and a disadvantage in sporting situations. Can you explain how or why that is the case? Well, the advantage is that it can be hard to move or hard to slow down to stop a body. Quite good, this is good in rugby and maybe basketball and maybe netball if you're going to collide with people, but not so good where agility is needed, e.g. gymnastics. So in sports where you're moving and you want to be able to keep going, as in rugby, when you've got the ball, you want to be able to keep going. You want to continue moving. So having a greater mass and greater inertia is an advantage there. We're now going to look at the tennis serve and Newton's first law of motion with that. So here's my friend Roger Federer. Where do we see Newton's first law of inertia or first law of motion, it's all the same thing, being applied here? So firstly, the ball isn't going to go anywhere unless he throws it up, so the ball will be in a state of inertia in his hand. The ball toss up will go straight up and then down to the ground unless the direction of its motion is changed by hitting it. So firstly, the ball is in a state of inertia before it moves. And then the law of motion, the ball is going to keep going in a straight line or in the direction that it was sent until or unless something hits it. So it will go, when he throws it, it will go straight up, then gravity will act on it and it will come straight down to the ground unless Roger applies a force to the ball and the racket is applying a force to the ball. And looking at the racket will not move unless there's a force applied to the racket. So as he moves his arm, that will apply a force to the racket, which is then transferred to the ball. Right, now we're going to look at Newton's second law. The second law of acceleration. When a force acts upon an object, the object accelerates in the direction of the force. And the acceleration is proportional to the mass of the object. So the heavier the object, probably the slower the acceleration. It's like it's like when you're at the traffic lights and you're sitting alongside a big truck, and you're on a motorbike or a car. Your car has got less mass than the great big truck, so you will accelerate faster. So Newton's second law is saying that the harder you hit the ball, the faster and possibly further it will travel, or the softer you hit it, the slower and less further it will travel. And the less distance it will travel. The mass will accelerate in the direction the force is applied. How does Newton's second law apply to a basketball jump shot? Well, firstly, we knew Newton's first law applied because the ball will stay in his hand unless a force is applied to it. And now the second law, this can be applied to the jump shot. As the player applies a force on the ball to accelerate it out of his hands, it will cause the ball to suddenly gain momentum towards the goal. Page 67 in your workbooks, please. Right, the first question is, consider a table tennis ball, a hockey ball and a shot put. If each is hit with the same amount of force, which one accelerates the most and why? So if you're going to hit them all with the same amount of force, which ball is going to travel the furthest or accelerate the most? You can write down, I hope you've come up with the answer yourself. The table tennis ball, because it has less mass. All right? The table tennis ball is lighter and has less mass than a hockey ball and less mass than a shot put. If we strike the hockey ball with increasing amounts of force, what happens to the ball? So if you're hitting it with increasing amounts of force, so it would naturally, as you increase the amount of force, it increases the acceleration as you increase the force. So we can summarize this equation by saying as force increases on a constant mass, acceleration increases. If a constant force is applied to a progressively smaller mass, acceleration increases. So if as force increases, looking at these different size balls here, if we applied increasing force to the ball would accelerate at an increasing rate. And if the same amount of force is applied to the big ball, this one here, and then the small ball, equal amount of force applied to each ball, the ball with the smaller amount of mass will accelerate greater. So if you double the mass of the soccer ball and you did not double the force applied, what would happen to the acceleration? Which ball would travel fastest? So we've got the same amount of force going there as here. Whoops, what happened there? Turn that around a little bit. Can I turn it around? Here we are. Get it right. There we are. That's a bit of force there. And I've got another bit of force going equal amount there in the same direction. Those are equal forces. Okay. Now they're equal forces. Which ball is going to accelerate at a greater speed? So the answer would be the smaller soccer ball, the average size soccer ball, because it has less mass. Okay, forces measured in newtons. So here we've got two identical objects with 10 newtons being applied here. Oh, don't want to move that round. 10 newtons being applied to it there. And here we've got 60 newtons being applied. Does that look bigger? Bigger force? Which one will accelerate fastest? They're equal mass, two identical objects. This one here's got 10 newtons. This has got 60 newtons of force. Of course, this one here is going to accelerate fastest. Oh. Can you read that? So here we've got a question: what would happen if two forces acting on an What would happen if there were two forces acting on an object in opposite directions? Looking at this diagram, I would say this force here is the larger force. Let's get a bigger, yeah. This force here is the larger force, and this is a smaller force. So this fellow would actually be accelerated in that. Oh, it would twist him round. He would travel in. Whoop. This is fun. Two hands on him. Yeah, travel in that direction. If they were equal forces, okay, so if the forces were equal forces, whoop, he actually wouldn't go anywhere, would he? Those are meant to be the same size. They don't look very equal to me. Okay, I've got it right now. I think they're pretty equal looking forces now. So if they were equal forces, he wouldn't travel anywhere. Right, question 3. Consider this situation here where a golf ball is travelling towards the green and is hit by a sudden gust of wind from the right. Explain what would happen to the flight path of the ball using Newton's second law as justification. So the wind force is being applied. It may be a force greater than the ball, causing the ball to move in the direction the force is applied. So the ball has been hit in that direction. Nice, get this right. And the wind gust has come along from this direction. So the ball is going to be, whoops, move that right. That's the wind gust. So it's going, the resulting path of the ball is going to be like that, which is Newton's second law. The wind is a force is being applied to it, that's the blue arrow. Another force is being applied to the ball, that's the wind gust, and that's changing the direction of the flight path. Here we go with a volleyball setting themselves up to spike, a volleyball player setting the ball and spiking it over the net. So how can we apply Newton's second law to this? That's a spike over the net. So the volleyball will be struck by the player, that's Newton's second law, because the ball's mass is constant, that is, the ball is just always one weight. The greater the force applied by the player, the greater the acceleration of the ball back over the net. And the ball will travel in the direction of that the force is applied, which is hopefully down and over the net. And finally, Newton's third law, page 66 in your books. For every action, there is an equal and opposite reaction. So when you apply a force into the ground applies a force back to you, and there's also a force going into the ground. Here we've got two lots of forces going on. You've got the basketball player applying a force to the basketball. I might draw it like this. Oh no, see how I go. In that direction. And then there's an equal that's the action force, the red one. And then the blue arrow, which I'm going to put here, is a reaction force. That is not the one I want there, though. Okay, so here we are. We've got the reaction as the blue one, which is the force coming back into your hand. And down here, the ball is now pushed onto the ground. So that is the action force going onto the ground. And then there's the reaction force, which causes the ball to bounce back again. Okay, I'm not sure what's quite happened to this picture here blocking our view. But when an object exerts a force on a second object, the second object exerts a force equal in size in the opposite direction. So the sprinter sprinting through the ground, to run, your foot is actually applying a force towards the ground, and then the reaction is you accelerating off the ground. And here we've got the ball being bounced on one of those catch ball things there, and then the ball reaction, it coming back again. So the sprinter coming out of the blocks, they exert a force into the ground through the blocks, and the blocks exert an equal and opposite force back, propelling the sprinter out of the blocks. The initial input of force is known as the action force. That's this one here. And the force applied back in the opposite direction is the reaction force. There we are there on the key. You can draw those two forces onto your sprinter, and don't forget to label them action and reaction. And number 4, we challenge for you here is looking at those diagrams, draw in the action-reaction force pairs on the illustrations in your book. Looking at this jump shot, it looks like here. Ground reaction force. If the athlete exerts a force on the ground in order to push off, the ground will exert an equal and opposite force on the athlete, pushing them into the air. The first force of the athlete pushing into the ground is called an action force. The second force is the reaction force. So the ground supplies opposing force. So that's how you can jump into the sky. You're doing when you're doing your jump shot. It's Newton's Newton's third law. Question 5 in your books. How does the high jumper get the power to jump so high? Well, they apply as large an action force into the ground as possible, and the reaction force propels them upwards. There are other important factors in the execution of a high jump. They're both technical and physical. High jumpers are usually very tall and swing the arm upwards strongly at the instant of takeoff. Explain how these would help in the execution of a high jump. Well, the tall jumper means the high centre of gravity, so the greater the input of force, the greater they can potentially jump. And the upward swing of the arm at takeoff also raises the centre of gravity even further. So if their centre of gravity is high to start with, and with the arms going up, it's moving the centre of gravity upwards. So it makes it easier for them, a bigger advantage for them with their high jump. How can you apply this to the volleyball spike? Think about that. Right, how does Newton's third law apply to a basketball jump shot? Well, when a force is applied, there is an equal and opposite force applied back. Whoops, here we go now. Newton's third law applying to the basketball jump shot. When a force is applied, there is an equal and opposite force applied back. This occurs in the jump shot when the player applies a force onto the ground to begin the jump. The ground then applies an equal and opposite reaction force against the player, causing them to accelerate vertically off the ground. Newton's third law also applies to the force that the player applies to the ball when shooting. When force is applied to the ball applies an equal and opposite reaction force against the player's hands. The ball will then move while the player remains in the same position due to their mass being greater than that of the ball, which is Newton's second law. Because the player has got more mass than the ball, the player doesn't move, but the ball does move. So let's finish off looking at Newton's laws. The first law, which is the law of inertia, the ball will remain at rest until a force is applied to it. The second law of acceleration, the greater the force applied, the greater the acceleration of the ball. And the third law, the runner applies an action force on the ground, and the ground applies a reaction force back.